Whenever we conduct a hypothesis test, we start with the assumption that H sub 0, H naught, is true. The null hypothesis is a true statement. That's our starting assumption. The conclusion of a hypothesis test will require us to decide between rejecting the null hypothesis, which means we have enough data, we have enough evidence to discredit the assumption made by the null hypothesis, or failing to reject the null hypothesis. In that scenario, we maintain the assumption stated by the null hypothesis. We'll get into conclusions more, but something to notice here is we are only making a decision about the null hypothesis. We either reject it or fail to reject it. And now we want to take a look at some of the outcomes that can occur after we make that decision. Assume we want to test the hypotheses, the null hypothesis, that the population proportion is equal to 0.5, and the alternative hypothesis that the proportion is different than 0.5. There are 4 possible outcomes from conducting this test. First, we'll start with if the truth is that the population proportion is equal to 0.5. If that's the case, and we conclude that P is equal to 0.5, then we reached the correct decision. If we conclude that P is not equal to 0.5, when in fact it is, then we were committed what's referred to as a type 1 error. And these errors are dictated by our choice with the null hypothesis. So if we end up concluding that P is not equal to 0.5, that would occur if we rejected the null hypothesis. So we conclude the alternative hypothesis that it's not equal. If we fail to reject, then we maintain the assumption of the null hypothesis. We conclude that the proportion is equal to 0.5. And then depending on whether that's true or false, we end up committing a type 1 error or end up with the correct solution or correct result. If the truth is that P is not equal to 0.5 and we reject the null hypothesis, meaning we conclude that P is not equal to 0.5, then we reach the correct decision. If we conclude that P is equal to 0.5 when it's actually not, then we committed what's referred to as a type 2 error, or I should say a type 2 error occurred. We have 2 Greek letters, alpha and beta, which represent the probability of a type 1 error and the probability of a type 2 error, respectively. A type 1 error, again, occurs if we reject a true null hypothesis. A type 2 error occurs when we fail to reject a false null hypothesis. What's important to keep in mind is that we will rarely, very, very rarely, know if our ultimate decision on rejecting or failing to reject the null hypothesis is correct or not. Because that would mean that we actually know the true population value. If we know that, then there's no need to go through this process of conducting a hypothesis test. All we can do with inferential statistics is draw the best conclusion based on the data available. If we have good data, if we have a lot of data, there's a good chance that our final result will be correct, but it's likely that we never know, and we just have to trust these really good guesses that we're making. We can help ourselves along the way by limiting both alpha and beta, meaning reducing the probability of those two types of errors. Alpha in a hypothesis test is referred to as the significance level. And it's related to confidence levels that we had with confidence intervals. 1 minus alpha is equal to the confidence level, or the confidence levels that we were dealing with and with confidence intervals. So alpha being equal to, say, 0.05 is the same thing as a confidence level of 95%. Oh, made my notes disappear for a second there. The nice thing about alpha is that we just get to choose what it is. There's no restriction on it, really. We tend to place restrictions in that we limit alpha to be less than or equal to 0.1. We just don't want it to get very big because that's increasing our probability of a type 1 error. And common values are 0.01, 0.05, and 0.1. 0.05 is sort of the standard value that we would choose for alpha for a hypothesis test. 0.1, which is larger, could be used in cases where we have less severe circumstances occurring if we're wrong. And a value of 0.01 or smaller could be used in cases where we have more severe repercussions if we end up making a wrong decision. So if we're dealing with life and death situations, will a medication help people survive whatever scenario, cancer, some disease, something like that? If we want more, if the cases are more severe, if we want more certainty, we make alpha smaller. Beta is controlled by increasing what's referred to as the power of a test. Power is a more complicated concept. We won't go into it much, but one way to increase the power of a test is to increase the sample size. The larger our sample or the more data values that we're considering, the more power our test has. That's a good thing. It's reducing error. There are some test options that can increase the power of a test. Those are a bit beyond the scope of this course, but there are other opportunities out there. And another option is to increase our value for alpha. Alpha and beta share an inverse relationship. Meaning as one value gets larger, the other gets smaller. So a larger value for alpha translates into a smaller value for beta, but they're both probabilities of error, so we don't want to just choose a really large value for alpha. But it also explains why we don't necessarily choose incredibly small values for alpha. 0.01 is sort of a small value for alpha. We could choose something even closer to 0, but as alpha continues to get smaller, beta would continue to increase. So there's sort of this balancing act going on between alpha and beta, but in simple terms, the easiest way to reduce beta and increase the power of a test is to try to get larger samples.